Hello everyone, welcome to Artistic Atom channel. I'm Fatima and this is part 4 of organic reaction series. So in the previous session, we have completed free radical substitution reaction, nucleophilic substitution reaction. In this session, we will complete electrophilic substitution reaction. Before going ahead and understanding its exact mechanism and example reactions, let us first understand the meaning of this term. So this term consists of these two subterms, that is electro and philic. Electro means electron and philic means loving. So this species, since it is electron loving, it gets attracted towards the electron rich reactants. That's why this species carries positively charged. Since it is positively charged, it is electron deficient, hence prefers to react with electron rich reactants. That's why only aromatic compounds they undergo this reaction. Now, what could be the possible reason behind only aromatic compounds undergoing electrophilic substitution reaction? Well, the first reason is that these aromatic compounds, they are highly electron-rich species. Secondly, these aromatic compounds, they are very stable. Since they are very stable, when they react with an electrophile, they lose their aromaticity, but at the end of the reaction, they regain their aromaticity and become stable again. That's why it makes them as a suitable reactant for the electrophilic substitution reactions. Now let us understand the conditions for aromaticity. Well, using this checklist, you will be able to easily determine whether the given structure is aromatic in nature or not. Well, this is very useful in order to determine which structures or which compounds will undergo electrophilic substitution or not. Well, because if the compound is not aromatic, then it will not undergo electrophilic substitution reaction. So this is the easiest checklist that you can follow in order to determine the aromaticity. So let us take an example in order to understand how to use these steps. So here I have taken an example of benzene. So this is the structure given and we have to check for the aromaticity. So first step is to check whether the given structure is cyclic or not. As you can see over here, this chain, this carbon chain is closed. That's why I will confirm that this given structure is cyclic in nature. So this step is done. Now the second step is check whether all the carbon atoms in that particular structure or in that ring, okay, in that ring. So all the carbon atoms in that particular ring are sp2 hybridized or not. So here is the structure and we have to check the hybridization. Now the question arises how to check for the hybridization. It is very simple. You just have to check for the sigma bonds. So once you have got the structure, just count the number of sigma bonds. According to the number of sigma bonds, you will get the hybridization of this particular carbon atom. So when you have 4 sigma bonds in the given structure, the hybridization of that particular carbon atom is sp3. If you have 3 sigma bonds, then the hybridization of that particular carbon atom is sp2. If there is just presence of 2 sigma bonds, then the hybridization of that particular carbon atom is sp. So here we are not bothered of sp and sp3 hybridization. Here we are interested in sp2 hybridization. So let us check for sp2 hybridization. So here I have selected this particular carbon atom which I have marked over here. Now let us check for the bonding. So here are the 4 bonds of this carbon atom. So I can see that this bond is sigma bond, this bond is also sigma bond, this bond is also sigma bond, and this bond is pi bond. Now how you will get to know whether the bond is sigma or pi? Well, it is very simple. If you have just single bond, then these bonds are sigma bonds. If you have double bonds, then out of these 2 bonds, one is sigma and other one is pi. If you have triple bond, then 2 bonds are pi bonds and the third one is sigma bond. It is very simple to determine. So in conclusion, I can see that I have 3 sigma bonds over here. So since I have 3 sigma bonds, this means this carbon is sp. to hybridize. Similarly, I will check for this carbon, this carbon, this one, and this one, this one. So I can see that all the carbon atoms, they are sp2 hybridized. You have to check for all the carbon atoms in that particular ring. So here we are done with the second step. Now the third step is to check for the planarity. It is very simple. Since we have got the hybridization as what, sp2, we just have to understand this. Then it is very simple to conclude what is the planarity of this particular compound. So I can see that in sp2 hybridization I have s orbital and 2p orbitals. So we in totality we have 3p orbitals, only 2 are undergoing bonding. Okay, one is not undergoing, the third one is not undergoing hybridization, because the hybridization is what, sp2. So only 2p orbitals are undergoing hybridization. So I can see that out of these three, only 2 are undergoing hybridization with this s orbital. So they will form this particular geometry. Third one will remain as non-bonded. Okay, it is not involved in the hybridization since it is not undergoing any bonding. So I can see that in conclusion, I can see that this is what the geometry of sp2 hybridized orbitals. So this geometry is what, trigonal planar geometry. So we can say that if the carbon atom is sp2 hybridized, this means it is surely planar in nature. That's why we check for the hybridization. If all the carbons, they are sp2 hybridized, this means the whole structure is planar in nature. So as you can see over here, this is how the structure, you can see this is the structure of benzene, and it is completely planar in nature. So we can conclude that this structure is planar. Now let us check for the fourth condition, that is it, the system should be fully conjugated. What do you mean by conjugation? Conjugation is nothing but presence of alternate double bonds and single bonds. As you can see over here, I have this double bond, then I have single bond, then double bond, then single bond, and then double bond. So this is nothing but the conjugated system. So it follows fourth condition also. Now the last condition is to check for the Hückel's rule. Now let us understand what is exactly Hückel's rule. So Hückel's rule is nothing but this formula. So this formula will give you the number of pi electrons. These number of pi electrons will tell you whether the compound is aromatic or not, because these number of pi electrons which are obtained after solving Hückel's rule are required for a compound to be aromatic. So if the number of electrons given in your structure matches with the number of electrons obtained after using this Hückel's rule formula, then you will conclude that the given structure is aromatic in nature. Now let us understand this rule in depth after applying it to the example that we were solving in the previous slide. So here I have this benzene structure, and in order to apply Hückel's rule, first we have to determine how many number of pi electrons are there in this benzene ring. So for that, let us first check how many pi bonds are there. So here I can see that there is one pi bond, second and third. So here I have three pi bonds, and we know that each bond, each single, suppose if there is one bond, each bond is made up of what? Two electrons. So this means here I have how many? Total of 6 pi electrons present, because each bond is made up of how many? 2 electrons. So I have 6 pi electrons present in my structure. Now if I check these number of electrons with the number of pi electrons that I have got after solving Hückel's formula, I can see that it matches with the number of electrons using Hückel's formula. So I can conclude that benzene is what? Aromatic in nature. So this means benzene follows all 5 conditions. Hence, we can conclude that benzene is aromatic in. Let us understand few more things about the benzene structure. Here I have drawn the structure of benzene. Now this benzene ring consists of a conjugated system, due to which these pi electrons can easily delocalize and result in the formation of this structure. These two structures, they continuously interconvert into each other, or we can say that these pi electrons, they continuously delocalize inside the benzene ring in order to stabilize the structure. structure. This particular effect is called as what? Resonance effect. And these two structures are called as what? Kekulé structures. Now, these pi electrons, since they are continuously delocalizing inside the benzene ring, we can draw a circle inside the benzene ring to show that these electrons are continuously delocalizing. You can even draw a dotted circle inside the benzene ring instead of drawing a full circle. It's up to you. Now, this particular structure is called as what? Resonance hybrid, and this is the most stable structure of the benzene ring. Now, in our previous standards or in our lower grades, we have learned that when we have a single bond, the bond length of that particular bond will be longer, and if we have a double bond, then the bond length of that particular bond will be shorter. So if we follow that concept, then this could be the possible structure of our benzene ring. But in reality, scientists have come to this conclusion after performing a lot of experiments. They have come to this conclusion that all the bonds in case of benzene ring are of the same length. Now, in order to confirm this, we can also determine the bond order that will also confirm whether all bonds are of equal length or not. Now, let us determine the bond order in case of benzene ring. Now, what is the meaning of this term bond order? Well, bond order means how strong the bond is. Now, how it will tell you whether the bond is stronger or not? Well, bond order is nothing but the number of bonds between the two carbon atoms. So, if the bond order is 1, this means there is just one single bond. And as we have discussed, that single bond is longer in length. That's why it can break easily. Whereas shorter double bonds, they are shorter in length, hence it is difficult to break them. So that's why we can conclude that these bond order will tell you how strong the bond is, because they will tell you the number of bonds between the two atoms. So here I have taken example of alkane and alkene. So as you can see here, I have determined the bond order between these two carbons. So since there is just one bond, one single bond, I will say that the bond order is 1. Here also bond order is 1. Here also bond order is 1. So if we determine the bond order over here, I can see that here it is 1. Here it is 2 because there are 2 bonds present, and here it is 1. So this is how we determine the bond order. Let us check the same in case of benzene ring. Now, since in case of benzene ring, we can see that these pi electrons or the pi bonds, they're continuously delocalizing. Hence, it is difficult to determine where is the exact position of these pi bonds. So that's why we take out the average to determine the bond order instead of directly just counting the number of bonds. And this is the formula that we will be using. So bond order is equals to the total bond value divided by the number of bonds between the carbon atoms present inside the benzene ring. Now let us do the calculations. So let us find out the bond value. So how you will determine the bond value? It's easy. So you just have to check for the contribution of each bond. What is the contribution? Contribution of number of electron pairs. So if you have a single bond, then the contribution will be 1 electron pair. If you have a double bond, then the contribution will be what? 2 electron pairs. If you have triple bond, then the contribution will be 3 electron pairs. So this is how you will calculate the contribution. So let us calculate it in case of benzene. So here we have 3 single bonds and 3 double bonds. So since we have 3 single bonds, so it will be what? 3 into 1. 1 is nothing but the contribution of each bond. So since we have 3 bonds, so it will be 3 is into 1. So that this will be equivalent to what? 3 electron pairs. Similarly, we will do for what? Double bonds. So 3 double bonds. So the contribution for double bond is what? 2. So 3 into 2, that is equivalent to what? 6. So the total bond value will be what? Or the total contribution will be what? 3 plus 6, that is equivalent to 9. Now the next step is to substitute the values. So here I have got the value of the total bond value as what? 9. Now let us find the number of carbon-carbon bonds. So I have total 6 carbon-carbon bonds present in the benzene ring. So it will be 9 upon 6. So if we do the calculation, it will be what? 1.5. So the bond order is what? 1.5, because the electrons are continuously delocalizing inside the benzene ring. And if you do the same, so you will see that for all all the bonds, the bond order is what? 1.5 only. That's why all the bonds in the benzene ring are of the same length. Now let us check the question. So question 1 is, which of the following is true about the structure of benzene? So the first statement is benzene has delocalized structure of pi bonds around its ring. So we have discussed that this is what the benzene ring, and here is the resonance hybrid, which shows that the electrons or the pi electrons are continuously delocalizing. So this first statement is absolutely correct. Now the second statement is each carbon to carbon bond has bond order of 1.5. This is true because we have done the calculation and we have got the bond order as what? 1.5. So this statement is also true. Now the next is what? Benzene is susceptible to attack by nucleophiles. Well, since benzene ring is aromatic in nature, it undergoes only electrophilic substitution. Hence, this statement is absolutely incorrect. So if we check our correct option, then this will be the correct option for this particular question. Now let us understand the mechanism of how exactly electrophilic substitution happens. So here I have taken aromatic compound. So here I have taken example of benzene, which is reacting with this particular electrophile. This is electrophile and it carries what? Positive charge. Why? Because it is an electron deficient species. Now these pi electrons will attack on this particular electrophile, and this is what we get. Now this structure will continuously these bonds will continuously delocalize in order to stabilize the structure. Now after this, let us do the rearrangement in order to stabilize this particular carbocation intermediate. So when we add base, so what will happen? This base will abstract this hydrogen and this bond will shift, or these two electrons will shift over here, and this is what we get as the substituted product. So this is what the mechanism of electrophilic substitution reaction. Now let us take an example. So here I have taken example of nitration of benzene ring. So here is the benzene ring, and the reagents that we will be requiring for this particular reactions are concentrated HNO3 and concentrated H2SO4. Now concentrated HNO3 plus concentrated H2SO4 together is called as what? Nitrating mixture. Now the temperature that we have set is what? 50 degrees Celsius. So it will result in the formation of what? Nitrobenzene as the product. Now let us understand the mechanism behind, so that we understand how exactly the nucleophilic substitution reaction occurs. Now let us understand the mechanism. So the first step is the protonation of nitric acid. So here nitric acid is not acting as an acid, it is acting as a base, and H2SO4 is acting as what? Acid. So H2SO4 will lose H plus ions, and this HNO3 will abstract that particular H plus ions and result in the formation of this species. Now in the next step, as you can see, if I draw this structure, if I draw the open structure of this particular species, it will look like this. Now in the next step, what will happen? There is a formation of the electrophile. Now in order to form that electrophile, we will use the species that we have got in the first step. Again, the lone pair of this particular species attack or we can say abstract the hydrogen ions from the H2SO4, and as soon as it abstracts, it will result in the formation of this species. Now since there are two positive charges, we have to do the rearrangement and stabilize the structure. So this bond will shift over here and this bond will shift over here. So this will leave as what? Water molecule. Now here we have got what? The nitronium ion. Since it is carrying positive charge, this will act as what? An electrophile. Now remember that H2SO4 will remain in the solution because this reaction is ongoing. Now in the third step, what will happen? Benzene ring will attack on the electrophile that we have got in the second step. Now these pi electrons will attack on this particular electrophile, and this is what we get. Now we have to do the rearrangement in order to stabilize this particular carbocation. So the HSO4 that we have got in the previous step, which were there in the solution left from the second step, that will abstract the hydrogen atom over here, and this bond will shift over here, and this is what we get at the end, to which we call it as what, nitrobenzene. So this is how exactly the mechanism happens in case of electrophilic substitution reaction of benzene. Now let us solve one question based on the concept that we have learned in the previous slide. So the question 2 is 4-nitrophenol can be produced from phenol. What is the name of the mechanism used to make 4-nitrophenol? So here you can see that we are making nitrophenol. This means we are adding nitro group. That is, we are doing nitration of phenol. So when we are doing nitration of phenol, we require what? Nitrating mixture. So nitrating mixture is nothing but what? Concentrated HNO3 plus concentrated H2SO4. In step 1, what will happen? This will act as base and it will abstract the H plus ions from this H2SO4 and results in the formation of what? This species. From this species, these two lone pair of the oxygen, they will again abstract one of the hydrogen from the H2SO4 and result in the formation of this particular intermediate. Now it will undergo in rearrangement and result in the formation of nitronium ion. This will act as what? An electrophile or the electrophilic species. Now what will happen? This electrophilic species will react with phenol, because this benzene ring in the phenol is going to attack on this particular electrophile and result in the formation of what? Nitrophenol. Now remember that since there was involvement of benzene ring, that's why this particular mechanism is what? Electrophilic substitution reaction. Now the other point that you should know is whenever benzene ring or any of the derivative of the benzene ring is undergoing any of the reaction, there is possibility of three products. That is, there can be formation of para substituted product, there can be formation of ortho substituted product, there can be formation of meta substituted product. Okay, and also you may in exam you may have a question where they are asking which is the major product. There you have to use a concept based on electron donating and electron withdrawing group. So if you have an electron donating group attached to the benzene ring, as you can see, this particular group has donated its electron to the benzene ring. Okay, so this particular group, this OH group, is called as what? Electron donating group. So if you have an electron donating group, it will result in the formation of ortho and para substituted product. Okay, now out of these two products, there will be one major product, another will be what? Minor product. Now how to decide which one is the major and which one is the minor product, that I have explained in detail in the video that I have made. I'll be uploading that video in the next week, so stay tuned. So in conclusion, the answer for this particular question is what? Electrophilic substitution, which we have discussed how you will get this, because the benzene ring is involved and benzene ring will undergo electrophilic substitution only. Now the next question is, benzene can undergo nitration to form nitrobenzene, which we know because we have discussed it in the previous slide. Which of the following statement is not correct? So we have to mark the incorrect statement. So let us check all the statements one by one. So when we are doing nitration, so statement A is concentrated nitric acid act as a base. So yes, we have discussed this, that whenever we are having nitric acid and H2SO4 undergoing nitration, so there nitric acid acts as a what? Base, because it is going to abstract the H plus ions produced by H2SO4. So it is acting as a base. So this statement is true. Now the next statement is a nitronium ion act as an electrophile. That is true because we have learned the mechanism and we know that there is formation of nitronium ion which will act as an electrophile, and then the further reaction will happen. So this statement is also correct. Now the next statement is HSO4 is produced in the formation of the electrophile. So yes, we have discussed this step when we are forming electrophile. For nitration, there is this HSO4 minus which is getting produced during the process. So this step is also correct. So this means this last statement is going to be incorrect, and it is clear that we are nowhere using aluminum chloride during the reaction. So that's why this step is absolutely incorrect. So with this, we have completed our session. Thank you so much for watching. Do like, share, and subscribe to my channel, Artistic Atom. So we will see you in the next session. And also, I will be uploading video based on this major and minor product, and also on which particular position the substituents will go in case of the reaction wherever benzene ring is undergoing any reaction, okay, or the derivatives of benzene ring. So stay tuned and do check out that video.